Before we begin today's lecture, if you have any questions about the previous one, please feel free to ask. All right, nothing. Okay, then
السلام
that's
عليكم
good.
دكتور محمد.
Walaikum assalam.
Doctor, there is something I didn't understand yesterday, which is the probabilistic approach in the minimization. Uh, yes, in the loss minimization. I
Mm,
really didn't understand it. I understood that there are two types of approaches: the minimization loss and the maximum likelihood estimation, which is the probabilistic approach.
mhm.
This one I didn't understand. The
Okay,
probabilistic one.
all right. I will go over that briefly. I think Ali mentioned that he didn't cover that yesterday. Mm, Wait a minute. Okay, I'm sorry guys, but I don't speak Arabic, so you will have to bear with me in English. If at any point you feel lost, please feel free to stop me and then I can repeat it or go over more slowly. All right, just to confirm, you mean this particular thing, right?
Yes, please.
All right, okay. All right. So basically, what you guys mostly covered yesterday was that you covered the closed form of linear regression and also found out that basically you can, if you do the vectorization, you can write y as x transpose into theta, right? Till this is fine, right? Okay,
Yes.
perfect. Now, the problem is that usually when you have the data in the real world and Usually the data is in the form of continuous format. So you will notice that you don't see the data. There is usually some noise in the data, and you won't see the output to be exactly this. So basically, you have some sort of noise added to it, and we can express it with some epsilon, and this epsilon is just a normal distribution with mean zero and some standard deviation theta, sigma, which is just a very low number. Okay, so if you express y, express y in this format, then y also becomes a part of a normal distribution such that the mean would be this thing because this is just 0 plus x transpose theta. So it comes out to this thing, and the standard deviation would be the standard deviation of the epsilon. Till this, is it fine?
Yes.
Perfect. Okay. I just noticed this. This thing is wrong here. So this should be once again x transpose theta. Okay. So the probability of y given some x would be will be a normal distribution, will be represented by a normal distribution with mean x transpose theta and with the standard deviation of sigma. Okay. So this is just representing our linear regression in the form of a probability distribution. Okay. There is nothing fancy going on here. All good?
All good.
Perfect. Okay. So now you know that if we have our data D, the distribution of this data D is just the distribution, the cumulative product of the probability distribution of all the individual data points. Okay, and in each individual data point we have a x and we have a y. Okay, make sense? So, so we can just decompose our whole data set into this product of distribution. This is only assuming if all the samples are identically independent, right? So, what this means is that, for example, if I have sample one, uh, the, the sample two shouldn't be dependent on the sample one. Okay? So whatever value I get for sample two should not depend on what the value was for sample one. Okay, make sense? And then using just simple Bayes theorem, we can, you know, that the Bayes theorem is that if the probability of A given B is equal to probability of A and B divided by probability of B. Okay, so we just re, uh, re, take this to the other side and we open this up in this format, right? All good?
All good.
Let's move on. So now we know that as we have already expressed, this thing is just some normal distribution with mean x transpose theta and standard deviation of sigma or variance of sigma square. We know that the PDF of normal distribution is given by 1 minus sigma 2 pi into exponent minus mu minus uh, x square. Okay, so we just open this, we just replace the values here and we put uh, uh, the mean or whatever our desired value is and then our predicted value, right? All good.
Yes,
And
doctor.
next we just put this thing in this equation in the joint distribution. Okay, so this is our final expression. Right? Now, now we move on towards the maximum likelihood estimator. What maximum likelihood estimator means is that basically we are trying to get a model for which we will have the highest probability of getting the right answer. Okay, so let's say if this is the space of models or the space of estimator, sorry, the space of likelihood, we want a estimator which has the highest probability of getting the correct answer. Okay, so we just want a mean good value, right? And how we do that is that we just maximize the probability of the data given our estimator. So we are saying that we will predict some values with our estimator, and then we will see how much they conform with the original data set. Okay. So if the probability of the data is maximized, that means that this model or this estimator represents the data set best. Okay. Any confusions about this? I know it may sound a bit daunting.
No, it's clear, doctor, but the formula is a bit confusing.
Okay. Are you clear till this point? Uh, this form is fine, right?
Yes, yes.
Perfect. After that, there is absolutely nothing fancy. As I said, we want to maximize the probability of the data, right? So basically, we want to select a set of theta. We want theta such that we get the maximal value for this. Okay.
Yeah, it's
So
clear.
we are just gonna maximize this thing. Now when we maximize it according to theta, we notice that this term doesn't contain any theta. This term doesn't contain any theta. Only this term has some theta here. So if we just maximize this term, then the whole thing will be maximized, right?
All right, understood, doctor.
Perfect. So when we want to maximize this thing, we just need to just maximize this part. Okay. And as you might notice, this is just the same as the mean squared error. Okay. So the whole point of this is that the whole of the deep learning or the whole machine learning actually is based on this maximum likelihood estimation. Okay. Even neural networks are maximum likelihood estimators. So the whole point of this was to show that whatever closed form we had with the mean squared error is uh, is actually inspired from this maximum likelihood estimation, or they both are actually the same thing.
Thank you, Dr. Muhammad.
Perfect. Any other questions? Shall we move on to day two? All right. Okay. Let's move on to day two. Okay, we are doing everything fine on time. So today what we will basically study is logistic regression and then how we can do this logistic regression, the metrics, and then finally some optimizers. Okay, before we do uh, before we do that, we will briefly review what you studied yesterday, linear regression, and I will also introduce the concept of classification. As I said again, please feel free to stop me at any time. I like when sessions are more interactive. Okay, so just as a recap for yesterday, what we did or what you guys studied yesterday was something called linear regression. And what we are actually trying to do in linear regression is just trying to find uh, a line which best fits the some data samples. Okay, let me go to the pointer mode actually. Okay. So basically, we have these data points and we just want a line which best fit this data point. And how we do that is that if we do it using the closed form, we have a very nice expression. And basically, what we are trying to do there is that we are trying to minimize these residual values between the best fit line and the data point. Okay. For linear regression using the least square method, we have a closed form. So we just can so we can just plug in that formula and then we get the best possible line. Okay. Any questions so far? So what we do in linear regression is just uh, trying to predict some continuous value. Okay. So here our goal could be something like what is the temperature going to be tomorrow, and it can be, and as you can see, it can be any value. For example, it can be 80 degrees, it can be 80.2 degrees, 90 degrees. So it will be a continuous value between some specific range. You can have a range, you cannot have a range. Okay. The other kind of values that we can have is something called discrete values, okay, where we have specific categories. For example, there would be the question, will it be cold or hot tomorrow? Okay, then we can just define a threshold and say that, okay, if the temperature is lower than 70 degrees, we can say that it's cold. If it's higher than 70 degrees, we say that it's hot. Okay. Or we can have any other type of classification. For example, we give the model some image of a fruit and we ask and then we have some specific categories, whether this is an apple, this is a banana, or this is an orange. Okay, you can have any number of classes. The minimum is that you have two classes. So that thing is called binary classification. And if you have more than two classes, this is called multi-class classification. Okay. So just to clarify again, in the regression form, we have some data points and then we are trying to find a line which fits a data point. It can be some linear line or it can be a polynomial function with one or many curves. In classification, what we are actually trying to do, we have the same type of data or similar data, okay, and then we are just trying to find a decision boundary between them, okay. And what I mean by decision boundary is that basically it can be a line, a plane, a curve, whatever it is, and then you say that whatever is below that line, it belongs to one class. Whatever is above that line, it belongs to the other class. Okay. And once again, it can be a linear decision boundary. It can be a polynomial one, or it can be a very highly overfitted one. Did you guys discuss overfitting yesterday?
Yes, we did.
Perfect. So this clearly is a bad model because it is highly overfitting the data. It is also overfitting over the noise. So if we have some data point right here, it is very possible that we will misclassify it, or it will also perform very bad on the data point which it has not seen outside of the range. All right. As I said, the problem can be a binary classification, or it can be a multi-class classification. In multi-class classification, we have the same thing. We have different images in some space, or different data points in some space, images in this case. And once again, what we are trying to do is that we learn boundary for a specific class. Okay, so for example, we learn this specific boundary for the airplane, and we say that whatever is uh, behind that line, it belongs to the airplane, and whatever is behind this line, it belongs to the car class, and the same thing for the deer class. You can have as many classes as you like, right? This particular thing is a CIFAR 10 dataset, which has 10 classes actually. All right. Uh, as an example, for example, in binary classification, as I said, you just have two examples, two outputs. So it can be something like a spam filter, where you have an email and you want to classify whether it is a spam email or not a spam email. Or it can be something like fraud detection, where given some transaction or given some data point, you want to see whether this is a fraud or not. Okay. And in multi-class classification, as I already gave an example, you want to classify some data point into a number of classes. For example, you have an image of a fruit and you want to classify which fruit it is, or you have an image of an animal and you want to classify which animal is it. It is. And you can actually think of multi-class classification as a lot of uh, single classifiers or binary classifiers. For example, if I have this green line, what this green line actually means is that anything anything before the line belongs to the triangle, and anything after the line belongs to not a triangle. Okay. So this one particular line is still doing binary classification. Either is a triangle or not a triangle. And then similarly, we have the same thing for the square, we have the same thing for the cross. And when we combine everything together, we can actually distinctively classify each of the object, right? Okay, so how does this thing work? This thing is actually the same as what you studied in linear regression, and it is just actually a linear regression model in disguise. So in linear regression model, what you have is that the output is just the product of the weight matrix and the input matrix. Okay, but l- the only difference in logistic regression is that instead of having a continuous output, you want to have a probability as an output. Okay, for example, you want to have the probability of the object being from the plus class, or from the circle class. You can think of it like being a positive class and a negative class, right? Anything clear? Everything clear? Any questions? So just to clarify again, what we actually want in logistic regression or classification is some output which is in the range 0, 1. Why 0, 1? Can anyone tell me?
Probabilities cannot exceed 100%.
Exactly, because what we are actually trying to predict, or we are actually trying to have the output in the form of probabilities. We are just restricting our output to 0 and 1. So as I said, it's quite similar to what you have in linear regression, but we just change the range of the output. All right, and how we do that, we will study it in a bit. All right. So okay, so once we have the probability in the form of 0 and 1, then our next question would be how do we map it towards the binary trace? Okay, so let's say if we have only two classes, and then we can just say that okay, if the probability of the positive class is, let's say, 0.2, then most definitely the probability of the negative class is 1 minus 0.2, right? Okay, and this would be 0.8. So this means that the probability of negative class is higher, 0.8. So this object belongs to the negative class. And how we classify it, we can easily just define a threshold of 0.5 and say that if the probability of the positive class is uh, probability of positive is greater than 0.5, then we say that it's positive. Greater than equal to, or if it is less than 0.5, then it's negative. All right, simple as that. Now, the question is how we do that. As I said, logistic regression is very similar to linear regression. We do have the linear model, and then we just squash it. We squash the output of the linear model to the probability, and then given a threshold, we can decide whether this is a positive class or a negative class. Okay, and how we squash it? We do it using a special function. We will study it in a bit. But any questions so far? Do you get the basic idea of logistic regression and how classification would work?
Yes.
Perfect. All right. So now let's go towards the squashing function. So we can actually use any function, but it just needs to satisfy these two characteristics. One, the output should be between 0 and 1. Okay. Why? Because we want these to be probabilities. And second, it should be smooth and differentiable. By smooth, I mean that it should be continuous. There shouldn't be any jumps in it. And by differentiable, because we will need to uh, do gradient descent, which we will come to that in a bit. And it should be easily differentiable too, right? So to come up with this, we came up with a function called sigmoid function, and the sigmoid function is pretty simple. It does its expression is given by this formula. So basically, whatever value we get from our linear regression model by W transpose X, we just put it in this formula. We take the negative exponent of the value, add 1 to it, and then take the reciprocal. Okay. And why we do this function? Why we use this function? There are a number of reasons. For one, it uses the exponent function, which means that the differentiation would be quite simple, quite easy. Second, uh, if we set it up like this, we will see that we will always get a value between 0 and 1. I will come to that in a bit. And third, because it's continuous and its derivative have a very nice form. We will also try to derive this thing. First of all, how this thing works, okay? So let's assume your linear regression model gives you a very large value, let's say of 1000, right? If I plug in the value of 1000 here, it would be actually the exponent of minus 1000. If we are taking the exponent of minus 1000, it would be a very small value, right? When we add it to 1, we will get a value which is quite close to 1, right? And this thing will actually be equal to just 1, okay? So if you keep increasing the number to 2000, 10,000, 1,000,000, you will see that you will get more and more closer to 1, but you will actually never cross 1, right? Can everyone see that? All
Yes.
right. Similarly, it's the case for a very small value. For example, if we have z is equal to minus 1000, then minus 1000 with a negative sign would be positive 1000. And if we take the exponent, it would be a very large value. So 1 plus some very large value. Okay. So this thing would actually be closer to 0, right? If we keep keep having lower and lower value for z, we will keep approaching 0, but we will actually never cross 0. And if z is perfectly 0, then the exponent of 0 is 1. So 1 plus 1 is 2. So 1 by 2, we will get exactly 0.5. Okay. So this means that all the negative numbers uh, will have the sigmoid value less than 0.5, and all the positive numbers will have the sigmoid value greater than 0.5 and less than 1, of course. Any questions so far?
Clear, yes.
All right. Uh, do you need me to go over the derivation of this thing? Like why the derivative of sigmoid function is this?
Yes.
Yes.
All right.
Yes, please.
All right. Let's just quickly go over it. Do we have any space in the next slide? No. I need to add a slide. Hmm. It's not going out of this slideshow. You can still see my screen, right?
Yes, it is clear.
I think it's not. Sorry about that. All right. Sorry for the interruption. You can see my screen, right?
Yeah.
Yes.
Perfect. Okay. So we had the sigmoid function in this form, 1 plus e to the power minus z, right? Now, if we want to take the derivative, we will take it with respect to z. So it will be derivative with respect to z, 1 plus e to the minus z. We can write it like this. We just take this up, not up, but write it in the form other than the fraction, in the power form. Okay, everyone happy with this?
Yes.
Yes, that's fine.
All right. And now we can just use the simple power rule. So if we apply the derivative power rule here, so this would be 1 plus e to the power minus z minus 2, right? And then d to the dz, 1 plus e to the power minus z. Okay? And this would be just 1 plus e to the power minus z minus e minus z, because the derivative of 1 is 0 because it doesn't contain z, and then the derivative of e to the power minus z would be just e to the minus e to the power minus, right? Further simplifying, we can write e to the power minus z, sorry, minus here, and then this take this thing back to the denominator. Okay, separate it out. right? E to the power minus z, 1 plus e to the power minus z. Everyone happy with this?
You dropped a couple of powers. E to the
Yeah.
power, like 1 plus e,
So
all
it
to the
should be
power.
square here.
Yes, yes.
And it should be minus 2 here. Perfect. Everyone good? Okay. So you can see that this thing is clearly sigma z, right? Okay. So we can write this thing as sigma z. And the other one, we further need to simplify it. And one way to do that is we add 1 and subtract 1 here. Okay. So now it would be 1 plus e to the power minus z, right? We break this down again into two separate fractions. So it would be 1 plus e to the power minus z divided by 1 plus e to the power minus z, and sorry, minus, and then 1 by 1 plus e to the power minus z.
Isn't
Yeah?
e negative?
Yes, you are right. My bad.
But it's fine because you take the negative out of the way.
1, and then actually if we take negative sign common here, so this would be plus 1 and this would be minus 1, right? Let me just confirm. 1.
I think you forget the negative sign when you
I
take
made a negative sign mistake.
the derivative of the parentheses 1 plus e to the negative z.
Where?
The third step. The third step.
This one?
Yes.
And
Yes.
what are you saying here?
You forget minus here because it's minus 1 above.
Yeah, it is minus 1, but then we take the, yes, of course. Yeah, you are right. There will be minus 1 sign here also. And then if we do the minus minus, this just becomes positive, everything out. Okay, so this would be positive, and then this would be positive, this would be positive, this would be negative again, this would be, so this thing is 1, okay, and then this thing is sigma z again. And then we got this form, right? Thank you for pointing that out. All good? All right, perfect. Okay, so now we have the sigmoid function, but it only works for two classes where we just have the binary classification problem. What if we have the multi-class classification? For that, we have something called softmax, okay? And in this softmax, this is actually quite simple. Let's say we have a list of numbers, okay? Let's say I have some numbers like 2, 3, 4, okay? And now we want to we want to transform these numbers in such a way that the sum of all these numbers should be 1, right? The most simplest way to do that would be to divide each of the numbers with the sum of the whole list. Okay, so so it would be just 2 plus 3 plus 4, 9, right? 2 by 9, 3 by 9, and 4 by 9, right? Make sense?
Yes.
Now, if I take the sum here, I would get the sum equal to 1. So, so this would be just the simple maths. What we have now is something called soft maths. Okay. In soft maths, what we do is that instead of just dividing by the sum, we actually take the exponent and then divide them by the sum of the exponent. Okay. Can anyone think of any reasons why we are doing this soft maths instead of just this max thing?
I'd like to say it's easier to derive, but I'm not quite sure actually.
Yes, that is one of the reasons. It will because it has a derivative and it will be easier to derive. Otherwise, if we just use the simple max function, the derivative would be just 1 or 0. That's it. Okay. The other reason and the main reason is that what if the model predicts negative values, right? So let's say we have something like -2 here. Okay. So now the sum would be 7. Sorry, 5, right? Okay. So it would be -2 by 5, 3 by 5, 4 by 5. Technically, the sum of this list is again 1, but now we have negative values in the probability, right? Which is not possible. Okay. But if we have the exponent function, we will transform each of the negative values to some positive value. Make sense?
Yes.
Okay. The other thing is that what you might notice that, for example, here there are all positive values, and you just do the simple max thing. You will notice that, for example, if you do the soft max, the probability of this thing is 0.9, right? If you just do the simple maxing, the probability of this thing would be something higher than 0.9, let's say 0.95. Okay. So softmax actually smooths out the probabilities. You can of course change how much smoothing needs to happen by something else, which we add to this function called temperature. Okay, it's out of scope for now, but it is also an interesting concept where you can actually change how much smoothing needs to happen.
Is
Okay.
temperature related to simulated annealing?
Kind of. Annealing is something else where you actually cut off the excess values. This is just, for example, if you have this curve, it will just smooth it out to be like this. Okay. All right. So now we are done with the special function. Okay. So if you remember here, we were, uh, we were, we are now done. We already have the linear model through linear regression. We didn't need to think about that. Now we are done with the special function. We have the threshold classification, and now we can actually get the modus prediction in terms of probabilities. Now the question is, how do we learn the thetas? How do we learn the weights? Okay. So for that, we need a loss function. Previously, we were using the mean squared error, right? And technically, we can still use it. Okay, there is nothing stopping us from using it. But it wouldn't be the most appropriate thing here. Why? Because we actually want a loss function which works with probabilities and not just raw numbers. Secondly, we want the model to be penalized for when uh, we want the model to be highly penalized when it makes a wrong prediction. For example, if it predicts uh, 0.9, which means that it belongs to the other class instead of the true label of 0. Okay. If we were just doing mean squared error, the error would be 0.0 minus 0.9. So it would be just 0.9 square, which would be just 0.81. Okay. The scale of this error is very low, right? So that's why we want a loss function which will highly penalize the model for giving wrong prediction. And lastly, of course, we want it to be smooth and differentiable. Okay. And what we came up is that, okay, we will use the logarithmic function. And how we will do that is that we will define a log loss. This log loss will work in the form that, let's say if your true prediction is 1, sorry, if your true label is 1, okay, and the model predicts 1, right? So now you want the loss to be very low, okay? You actually want the loss to be 0, right? So if you take the log of the prediction, which is 1 here, what you would get? 0, right? So log of 1 is 0. So in this case, the model made the correct prediction. We got the loss of 0. But let's say the true label was again 1 and the model made a prediction. I am not able to write here of 0.01, right? By the way, there is a negative sign here. So the log of 0.01 would be a negative number. In this case, if we were taking log with the base of 10, we actually take log with the base of e or 2. But just to simplify here, let's say we take the log to the base of 10. This thing would be minus into minus 100, right? So we get a very high loss. Okay, makes sense?
Yes.
So this is the case when the true label is 1. What if the true label is 0? For that case, we have the second part of the loss function, which is of this form. Okay, so in this case, if the true label is 0 and the model makes the prediction of 0.01 again, okay, so it would be 0.01. It would be log of 0.99. Since this value is very close to 1, we will get the loss close to 0, right? And similarly, if the model makes the prediction of a, of a high number, let's say log of 1 minus 0.99. So once again, we would get log 0.01, which would be a high number, right? So we have the loss in two parts. One, when the true label is 1, and the other when the true label is 0. All clear? To combine both of these things, we can write them in a single line like this. When the true label is 1, we just multiply the whole thing with the true label itself. And when the true label is 0, this term will come into action, right? So if the true label is 0, this term will zero out, right? And only this term will remain. When the true label is 1, This term will zero out and only this term will remain. Is this confusing or is this clear? Any questions so far? All right. It's pretty simple, right? And one last thing is that this is for just one particular sample or one particular prediction. But let's say your model made more than one prediction. We will just take the mean of everything. Okay, we just add all of the losses for each of the samples and then divide by the number of samples. That's it. All right. Okay, so now we have the loss. Now we need to find the most optimal weights or the most optimal thetas. Now we are at the same point we were when we were discussing linear regression and we go to the closed form. Okay. But here, if you actually try to calculate the closed form by just equating the derivative to zero, you will realize that it's not mathematically possible. Okay. So you cannot get a closed form like you did in the linear regression. So for that, what we need to do is something called gradient descent. Did you guys discuss gradient descent yesterday?
I don't think so.
Okay. Did you guys discuss this loss curve, by the way?
No.
No.
Okay. So the idea is pretty simple. It's that for any particular value of W's, you can compute the loss function, right? You can compute the cost. Okay. And you would get some value, right? For example, for this particular W, you got this value, right? For this particular W, you got this value. Okay. For this particular W, you got this value, right? So what you will actually have is that for all the particular W's, you will have some loss function, or sorry, you will have some loss value, which is also called the cost. Okay. You will randomly start with some W. Okay. And what your eventual goal is to reach a W, which will have the minimal cost, right? Okay. So let's say we start with random initialization of W and we got this cost. Okay. Now we need to reach this W, right? But we don't know where this W is. Okay. We will only know this if we compute the cost for all the available W's and then find the minimum, which is not possible because W is a continuous value, so it can be any value between minus infinity to plus infinity. And if there are more than one weight parameters, then it just makes the whole thing more difficult, right? Any questions so far? So what we do here is that instead of finding all the W's and all the cost, we just compute the derivative of the loss function here. This will give us the direction of the steepest ascent. For example, it will give us this direction. Like it will say that, okay, in this direction, the gradient will increase. Okay. But we need to go towards the opposite side where the gradient is the steepest. So we just multiply the derivative or the gradient with a negative number. Oh, sorry, with a negative sign, right? So let's say our previous W was 5. Okay. For this particular W, we took the derivative of the cost function, and let's say the derivative of the cost function was something equal to something 2, right? Let's say 2. Okay. So we will just update our weight towards the uh, negative gradient. So we will do new W equal to W minus the derivative. Okay, so it will be 5 minus 2. So our new W would be 3. Okay, this is just an example. Any questions so far? And we will keep doing this. So for example, we were at this point, we computed the derivative and then we updated the W. We might reach this point. Okay, and then we will do this again if the derivative is a non-zero value, because if it is a non-zero value, it means that there is some more leeway here where we can go. If we reach at this point, then the gradient of this point would be actually 0, right? Okay, so we do have a convergence for a stopping point. We will keep doing this until eventually we reach this point. Now here there is a problem, okay, because this step size can be large. Okay, so let's say if your line is something like this, at this point the model will say that okay, make a very big jump. Okay, and you might make such a jump that instead of going here, you reach here. Okay, you actually cross the optimal point. In that case, what we do here is that instead of making the jump according to the exact gradient, we make a smaller jump. So we just multiply the gradient with a learning rate, and this learning rate is usually a very small number, to for example 0.01, 0.001, or even smaller. It depends on your particular setting or on your particular optimizer. We will discuss optimizers later. It's the time. Okay, we are good on time. Any questions so far? All gradient descent, learning rate? Yeah, please go on.
We use the learning rate to make it more dynamic steps.
We use the learning rate so that our step size or the jumps that we make are not abrupt. Okay, because if we don't use a learning rate, there might be the possibility that this thing will ask us to make a very big jump, and then we might actually overshoot the optimal point. Okay, so let's say this thing asks us to make a big jump and we reach here, right? And then we do this thing again, do the gradient descent again, and it will once again say make a very big jump, and we can come back here again. Okay, so we can get stuck in this loop where we actually keep overshooting the optimal point again and again. Make sense?
Yeah, but
Any other questions?
How to determine learning rate in the first place?
Ah, that's the question, right? So there is no actual proper way to say that, okay, this is the learning rate for this particular problem, right? But we can make a educated guess that we will need a learning rate like this depending upon some optimizer or on some problem. But usually the ideal way is to use a lower learning rate, something along the lines of 0.001. Okay. Or the other way is that you try a bunch of learning rates and then whichever performs the best, you choose that one for further training. And the one other way is to use something called learning rate schedulers, where you don't actually use one learning rate, but you use a schedule of learning rate. So for example, you say that, okay, at the beginning of training, I will use a learning rate of 0.1, but after some time, I will use the learning rate of 0.01. Okay, and you keep decreasing it as the training progresses, because you might notice that as we reach the W, then we need to make very small jumps so that we don't overshoot the optimal one. Okay, does this answer your question?
Fine. Yes.
All right. Anything else? All right. Okay. Let's move on. So I already highlighted the importance of learning rate. This is just the same thing. And just to clarify again that the differences between linear regression and logistic regression. For linear regression, we are actually trying to predict the continuous values, but for logistic regression, we are trying to predict a probability. We are trying to do classification. Okay, it says regression in the name, but it's not regression itself. It's classification. Okay. All right. Finally, we have some metrics. Like for example, if we have a model, okay, and now we want to see how good that model is, right? For linear regression, our metric was just that we measured the mean squared error. Okay, so so the lower the mean squared error we have, the better our model is. But here, since we are using something called log loss, we actually want to know in numbers how good our model is. Okay, and the most simplest way to do that is to just use accuracy. Okay, accuracy is just however many correct predictions the model by the total predictions made by the model. Okay, so let's say if I had 100 samples and the model correctly classified 90 of them, my accuracy would be 90 by 100, and it would be 0.9. I can of course multiply it by 100 to get percentage, so it would be 90%. Okay, but there is a problem with accuracy. Let's say I give you a model, okay, and I say that it has 95% accuracy. Okay, do you think you can just trust this number and it will be a very perfect model?
I don't think so.
Can you give me a reason?
There might be class imbalances, and the model is biased toward a certain class that is dominant in the dataset.
Exactly. Perfectly right. Excellent. So let's say you were trying to do spam and non-spam filtering, right? Okay. And all your data set had was that in your samples you have 95 uh, non-spam emails and only 5 spam emails. Okay. But your model was a bad model, and it made, for every input, it said that this is non-spam. Okay, so it made 100% non-spam prediction, right? In this case, our correct predictions will of course be 95. So we would get 95% accuracy. Make sense? But this is bad, right? Because let's say if we encounter a spam email, the model will once again make a prediction of non-spam, and this model is actually useless to us, right? It's not doing anything if it says every email is non-spam, even though it will have good accuracy on some particular test set. it is actually a useless model. Okay. So to rectify this, we actually have different metrics. I will come to those in a bit. Before that, in linear regression, we actually just wanted to minimize the mean squared error, and then that was also our metric. So we were actually minimizing the metric itself. Okay, why can't we do that here? Why can't we just minimize according to the accuracy instead of use the? Why do we have to use the log loss? Because if you have a look at the formula for accuracy, you will notice that this is not actually differentiable. Okay, and we need our loss function to be differentiable to do the gradient descent because we need the derivative to do the update, right? Okay. One last thing, I just want to mention that there are other names for this log loss also. So you might have heard of cross entropy or binary cross entropy. It's the same thing, it's just another name of log loss. Okay. All right. This we already discussed. Classification isn't always enough. For example, if there is, as Anas just mentioned, if there is a high imbalance in the data set, we might get a very high accuracy for some particular data set, but actually our model would be very bad, right? So to avoid these kind of things, we actually measure some other metrics, and two of the most common ones are precision and recall. Okay, precision is actually the number of true prediction the model makes out of uh, the number of correct true prediction the model makes, positive prediction the model makes out of all the positive prediction. Okay. Uh, Before I go toward this thing, let me just clarify one thing. So all the predictions can be classified into four forms: true positive, false positive, true negative, and false negative. Right? True positive means that the true label was 1, true label was 1, and the predicted label was also 1. Okay. False positive is that the true label was 0, but the model actually predicted it to be 1. Okay. True negative again would be that the true label was 0 and the model predicted it to be 0. Right? And false negative would be that the true label was 1, but the model predicted it to be 0. All right. So out of all of these four, this is a correct prediction and this is a correct prediction. This is correct, and these two are wrong. Right?
No.
Oh, my bad. Sorry. My bad. I thought this was false. True negative. I messed up the order. Okay. And this one is correct and this one is wrong. True negative and true positive are correct, and false positive and false negative are wrong. All right. Okay. So why do we need this? Because let's consider the same example of spam filtering. In that case, our model always made the prediction that if we consider that spam is positive and non-spam is negative, our model always made the prediction that the output is a negative, right? So in that case, our precision, actually, let's consider spam as positive because that will make explaining it easier. Spam is positive and non-spam is negative. Okay, so in that case, our true positive here would be just 0, right? Because the model actually never makes the spam prediction. And then 0 plus false positives would uh, would again be how many would that false positive? The doable was 0 and the model made the prediction 0. There would be then 0 and actually the precision in this case would come out to be 0. So this would be a very bad model. Precision actually would not be defined here. We would get error because we are dividing it by 0. So this is a very bad model. Precision allows us to identify models like that. But we also care about whether the model was able to capture all the positives. Okay, so in that case, we have something else which is called recall. This should be recall here. And here we just divide this thing by true positive plus false negative. False negatives are the ones where the true label was 1, but the model actually said that it was 0. Okay, so for example, this might be important. For example, doing cancer detection. The patient had cancer, but the model said that it didn't have cancer. Okay, so in this case, we want the model to have a very high recall. So basically, what we want is a model which has a high recall high, and precision to be high also. Okay, so we have both of these things, precision and recall, and then we can actually to get one consolidated measure, we can take their harmonic mean. Why do we take their harmonic mean? Because the harmonic mean is better for ratio. You can read more about that, and it takes this form. This thing can also be written as 2 into precision into recall divided by precision plus recall. All right. Any questions so far?
It's clear.
Perfect. It actually is fine, right? And I hope that you guys are not uh, confused or sleeping in the background. All right. So logistic regression is one form of classification models that you have. There are of course other models. Few of the most common ones I will just highlight here. You can of course read about them later. One of them is this sport vector machine. The concept is again very simple. we try to find in sport vector machines or sport vector models, we try to find a boundary such that it maximally distributes the both the classes. Okay, so we are actually trying to maximize the margin here. Okay, sport vector machines are also very commonly used for anomaly detection, where we are just doing one class classification. And basically, what we do is that we uh, either do a boundary like this, where we represent them in a higher dimensional space, or we do a boundary like this, where once again we are representing them in a high dimensional space. So there are two types, two different ways you can do this. You can represent your data in this form or in this form, and then you find some hypothetical boundary and say that anything within this boundary belongs to this particular class, but anything else is an anomaly. Okay. And this is very common in fraud detection. For example, if you are making some transactions, there might be a model in the background which is saying that, okay, this transaction correspond to the habits of this person, so it's fine. But let's say you suddenly make a very big transaction in some place where you are not normally present, so that would be highlighted as an anomaly. Okay, so that's SVM. Then we have something else called decision trees. You might have heard of them before. Decision trees are quite simple, and they they are also used for classification. And what you do is that at each stage, so it unfolds like a tree, and at each stage you ask yourself a question. For example, if you were trying to classify whether if this is a chicken or not, okay, so you can see that, okay, whether a given bird is chicken or not. Okay, so the first question would be, is it available to fly? If it's true, if it's false, and then if it's true, you ask another question: does it lay eggs? If it is false, then you ask, does it have feathers? And you actually keep asking yourself questions, and eventually reach some bottommost layer where you give the prediction. Okay, and yeah, that's it. The main problem with decision tree is that they do work very good, okay, but they can overfit very easily. Okay, so since you are making your question based on some training data, when you encounter some new data in the test set, you might encounter something which you haven't thought about before, and none of the questions seem right for it. Okay. So the decision tree overfit very easily. And the other problem is that if you don't have a very specific decision boundary like this, and you have some linear boundary going on where between the features, right? So this thing here will also cause problems. Okay. Can anyone guess why this would be a problem? Because then you won't be able to answer your question simply true or false because it will be true if x1 has 0.4 and x2 has some specific minus 0.4 and is higher, and x2 is higher than minus 0.2. But it will be false if x1 is 0 and x2 is minus 0.1. Right? So there is some linear correlation going on between x1 and x2, so you can't just make a very precise boundary. Okay. And then we have random forest, where you just combine a bunch of decision trees. These are actually very good models, and they are still very often used. So here instead of having just one decision tree, you have n number of decision trees. All of them make a decision, and in the end, you just do something like majority voting or just averaging, or just and then select the final result. Sorry. Okay. One important highlight here is that all the decision trees are trained independently. Okay. There is another kind of model where multiple decision trees are trained dependently, and that is called gradient boosting. So these are kind of a chain model. Okay. So you have one decision tree, it makes an output, okay, and then you have another decision tree which is actually just trying to minimize this output of the previous model, or not minimize, the correct the output of the previous model, and then you have another model which is trying to correct the output of the second model, and so on. Okay. And once again, gradient boosting models are quite good. There are different forms to it, XGBoost, there is ADA boost also. And yeah, they are still used in machine learning and actually are the top performing models there. Okay, let's take a break here. Before we go on the break, it will be a very short break. We will reconvene at 11 a.m. and then we will study optimizers, and then we will have our proper lunch break, and after that we will have the practical session.
Can I ask something?
Yeah, please come.
For the random forest and the one after it. So basically, in the random forest is saying that each tree is fed with different subsets and samples. For the other one, does it like take all the samples and all the features and train on it and then improve in the next version? Or does it
Yes,
also take subsets?
yeah. So in the random forest, you have the decision tree independent. Okay, so you have the data set. You train one decision tree over that, the other one, the other one. You train all your decision trees on the same data set. Okay,
Okay.
all right. In the gradient boosting method, you have your decision trees dependent on each other. So the first decision tree is actually trained on the actual data set. The second decision tree is trained on the predictions of the first of the first model. Okay. And similarly, the third one is trained on the predictions of the second model. Let me
Okay.
let me just give you a brief idea of how it works. Okay. So let's say you have a decision tree, or any model for for that case. Okay, and given an x, there is model M1. Okay, given an x, it makes a prediction of 1200. Okay, when the true value was 1000. Right?
Yeah.
Okay, so now you know that given this x, this model 1 will make a prediction of 1200. So you will calculate the residual here. The residual is just this thing, 1000 minus 1200. It will be minus 200. Okay.
Okay. So
Now, you will train your second model over this residue. So your second model, you will task your second model to predict the residue of the first model. So I will give it the same input x, and this time I will task the model to predict the residue. Let's say
okay.
it predicts minus 190. Okay.
Okay. Yeah.
Now, if I only had two models in my gradient boosting chain, I would be done here, and my final output will actually be the output of M1x. okay, and then minus, plus the output of M2x. Okay, in this case it would be 1200 plus, plus minus 190, and I would get 101, right? So now you can see that if I had just one model, it would have made the prediction of 12. When I have two models, I am now much closer to the ground truth.
Okay.
Make sense?
Yes, thank you. So it doesn't
Thank
pick like different feature subsets.
you. No, no, no.
Okay. Okay. Thank you.
All right. I will try to find some resources for you in the break and I will share it with you. I do have some resources uh, and then I will share it with you. Okay, let's take a break, but it will be a very small break. Please come back at 11 a.m. It's just 5 minutes, so it's a very small break, and then we will quickly go over the optimization and then we'll have our lunch break. All right, see you guys soon. All right, is everyone back? Let's begin. So, as promised earlier, we will now study this optimization. And what I mean by optimization is that, I highlighted this earlier. Okay. Yeah. This part is called the optimization. Okay. Where we are actually trying to learn how how to where we are actually trying to learn the weights and we are updating the weights. Okay. And this is the most basic form where we just take the gradient and multiply it with some learning rate. Okay. And then update the weights according to that. But of course, there are more sophisticated methods available which makes this jumping more smooth, more better, more faster, and we get the final weights. Okay, so we will just study those now, and then inshallah we will be done for the day. Then of course you will have the practical session. Any questions about what we studied before the break? All right. Let's begin. So as I said, optimizers are one of the main components of deep learning models. You will encounter them when you are training neural networks, any kind of neural networks, large language models, diffusion models, generative models, classification or models, any kind of neural networks. Okay. Uh, neural networks might be a bit unfamiliar to you at this point, but those are the main deep learning models available these days. We will study them tomorrow. Don't worry about that. But before we go over that thing, I just want to highlight the need and use of optimizers. All right. As I said, these optimizers are the specific method or technique that we are using to adjust or update the weights, right? This point I already highlighted when we take the gradient, it actually gives us the direction of the maximum increase. Okay, if we take the negative, then we get the direction of the maximum decrease. Okay, so if one direction is uphill, then definitely the other direction is downhill. Right? All clear?
Yes.
All right. Let's move on. As I mentioned earlier, by the way, the next list of slides is based on the CS 31 course by FALE at Stanford. It's also referred here. Uh, as I mentioned earlier, one of the most basic or the vanilla gradient descent is that we just evaluate the gradient and then we multiply it with some learning rate. We are calling it step size here. This is the same thing. Okay. Make it negative and then add it to the weights. Right? This is the vanilla gradient descent with no fancy thing going on. Okay. And what it does is that basically we just have, you can see my pointer, right?
Yes.
Let me
I
use
don't
the
think
bigger one.
so.
Can you see it now?
Yes, yes.
Yeah.
Okay, perfect. All right. So what happens is that, for example, this whole space is our loss function, this colored space. This would be our minimal point. Okay. So we start from some random W, let's say here, and then we start moving towards the steepest negative direction. Okay. So in this case, it might be towards this direction. So we go here and then we do the update again. We might go here and then we do the update again. We might go here. Eventually we will reach at this point. Okay. There is one other thing that I want to highlight here. It's not related to optimizer, but I just remembered that we didn't discuss this earlier. It's just the structure of the loss function or the loss graph, loss curve actually. Okay, so let's say uh, I have a loss curve like this. Okay, this is the most ideal loss curve where we have just one global minimum. Okay, so wherever we start, if we do the derivative, we will eventually reach. If we do the gradient descent, we will eventually reach this point, right? What if I had a loss curve like this? Okay? And let's say I start at this point. Okay. Now, my model or my weights don't actually know the whole structure of the loss curve, right? They only see the loss, the derivative of the loss value here, and it will say them to okay to move towards this direction. Okay, we will keep moving, keep moving. Eventually, we will reach this point, right? Make sense? And at this point, our derivative would be 0, right? And we will say that, okay, our derivative has reached 0, our model has been trained, we are done, right? But if you had access to the to the complete loss curve, you might find that there was an even lower point available here. This is the global minimum. Okay, so these things are called local minimas, and this thing is called the global minimum. Okay, but since our model started from here, it actually never explored this part of the loss curve, so it will never reach here. Okay, this is one of the problems that our model can get stuck in some local minima instead of the global minimum. In that case, we will not get the we will not get the best performance out of it. Okay. But this is also based on some luck because let's say if my model started from this point, then I would definitely reach here, right? Okay. Any question about this? Any confusions?
Doctor,
Yeah.
so it depends on the initial points.
Yes, exactly.
Shall we add more points to reach at the minimum?
Yeah. So this is one way. Basically, you can train the model multiple times and then use the model which performs the best. Okay. In that case, you would have random initialization for each of the model, and and even if a few model get stuck in the local minima, you might get a model which reaches the global minimum. That's one way. The other way is that we use something called stochastic gradient descent. I will come to that in a bit. But I just wanted to highlight this thing here because this is one of the problems that you might encounter later, or one of the things that you need to know that gradient descent is not the perfect thing because it can get stuck in some local minima and never reach the most optimal point. Right?
Uh,
Okay. So any questions up till this point? This This part is also clear, right? Where we start from some, let me go to the pointer mode again, where we start from some point and then eventually make updates to reach the to reach the minimal point. This is just in the 2D case. Here we are doing it in the 1D case where we only have one wave, here we have two waves. That's it. All right. Any questions? Okay.
Which point should we start from? How do we know that?
So whenever we train a model or whenever we train a neural network, we do something called random initialization. So we randomly initialize Ws. We do have a specific range where we initialize them. For example, we initialize them around the mean of 0, okay? But there are some models with a mean of 0 and I think the standard deviation is usually 0.1 or 0.0, 0.1 or 0.3. I'm not sure about that, but we usually initialize them in so that but there are those we have found that if we initialize the weights between 0 mean and 0.0 deviation, and particular Sorry, I dropped connection suddenly. Can you hear me?
Yes, we can.
Yes, doctor.
Okay, perfect. Let's begin again. Mm, Go to the mm, all right. So just to recap, what I was saying was that in general, we have random initialization of the weight parameters, the starting weight parameter, so we can actually start from any point in the loss curve. Okay, and then we update the weights and eventually reach the minimal point. All right. Okay, as I said, we use something called stochastic gradient descent. Why? Because there are two reasons. For one, because if we were to compute the gradient for the whole data set, and let's say our data set was very large, our training data set was very large. For example, we had 50,000 images, right? So computing the gradient for first of all, we have to do the pass of the model through all the 50,000 images. Then we have to compute the gradient for all the 50,000 images, and then we make an update. Okay, so this is a very expensive process, right? To rectify this thing, we use something called stochastic gradient descent or mini batch gradient descent. In mini batch gradient descent, what we do is that instead of using the whole 50,000, let's say 50,000 training data, we use just a batch of the training data. Okay, we use a small batch, like for example, 256, 32, 64, 128. There is no particular reason to have them to be powers of 2, but this is just a standard practice. This makes the whole thing, uh, the whole computation of gradient much easier, much faster, and it comes with the added benefit that it adds some noise to our updates. Okay, so for example, if actually the model was, if actually the steepest gradient for the whole data set was towards this direction, now since we are not computing the gradient for the whole data set, we might go towards this direction, yeah, or towards this direction. The advantage here is that this can help us sometimes get out of the local minima. Okay, so for example, if we were dealing with the whole data set, uh, the direction would be this. But if we were doing the mini batch descent, it might say that, okay, go towards this direction. Okay, and then we might overshoot the local minima and move towards the global minima. Of course, this also comes with the risk that we sometimes overshoot the global minima also, or we overshoot the minimum point. But if we keep training the model, we will eventually reach the minimum point. So it's not much of a problem. So yeah, so this is it. So now instead of having a very smooth loss curve, we will have a curve which would have some noisy spikes like this. But eventually we will see that the loss will decrease and we will reach the minimal point. Okay? Any questions?
It's clear.
Perfect. Okay. Once again here, I just want to highlight the importance of the learning rate. The learning rate can very much affect how good the model learns or how the model learns. Okay, so choosing a good learning rate is very important. So, for example, if you choose a very high learning rate, you might notice that instead of the model going towards the minima, it can actually overshoot and do very badly. For example, let's give an example of this particular very high minima rate. Okay. So let's say I have this loss curve, okay, and I'm at this point. If my learning rate is very high, I might jump, let's say I am at this point. If my learning rate is very high, I might jump here, okay. So now the direction is even steeper here. Now I will make an even bigger jump. Now instead of going towards the minima, I can go here, okay, and then I go here, and then I go here. So instead of uh, having lower loss at every next step, I will have a higher loss. Okay, so having a very high learning rate can actually uh, degrade the performance. Is it clear?
Yes.
Yes, everything.
Similarly, even if my learning rate is very high, but it's still high, I can also get stuck something like this where I just keep oscillating like this. I keep going here, then here, then here, then here, then here, then here, and I never reach the minimum point. Okay, so this would be the case of this green line, right? This green line. Okay, and then if my learning rate is very low, in that case, what the problem might be that my step size will be very small. So then I will take a very, very, very long time to reach the global minimum. Okay, so I will go from here, go very slow. Eventually, I will reach the global minima, but it will take up very long time and use a lot of resource, right? So that's why we need to have a good learning rate and which is not very high, not very small, and which leads us towards the uh, global minimum. And how do we get the good learning rate? As I said, there is no absolute way to do that. And for that reason, we use different kind of optimizers to lessen the dependency of the learning rate somewhat. And we use something called learning rate schedulers. Okay, we already discussed mini batch gradient descent. This is what the example I gave earlier. For example, if the true gradient direction was toward this direction, if I take a mini batch, I might go towards this direction. So there will be a possibility of noise. Okay, so instead of going towards the true gradient, I might choose a different path with some noise, but eventually you can see that I am moving towards the minimum. Okay, any questions so far? All right. Now there is a question. Okay, so as you can see that the standard gradient will actually move along the curve. Okay, it won't go from this point to the exact direction of the global minimum. It will always move along the curve. Okay, can we actually do this? Is there a way to go from this point and then get the direction directly towards the minimum? Okay, and for that we have something called Newton gradient descent, Newton gradient step. And what actually happens here is that instead of just focusing on the first derivative, we also compute the second derivative. Okay, so the second derivative is just the derivative of the derivative, right? And it does help. It makes the convergence very fast because now we move directly towards the direction of the minima instead of going along the curve. Okay, but why don't we use this? And why is it? Yeah, yes, Sans.
Uh, the Hessian the Hessian is a matrix. Which value of the matrix should we use?
So usually we just do the matrix multiplication here. So if this is a vector, and then we have the matrix. Wait, need to change to pen mode. Okay, so if this is our list of parameters, right? Vector of parameters. Okay, and as you correctly pointed, Hessian would be a matrix. Okay? So if you multiply both of these things, you would still get a vector out of it, right?
Yes.
Yeah.
Yes.
Okay. All right. So now my question is, why don't we then use it? Because uh, clearly it works, right? It will make the convergence very fast. The problem is that it's very expensive because computing this uh, second derivative is not a trivial job. Okay, so if my xn or if my weight parameters have n dimensions, then m dimensions, then the computing the Hessian will take the order of time complexity of m square. Yeah, because it has the dimension m square, right? And then if we and then you might also notice that there is the inverse sign over it. We need to compute the inverse of this Hessian matrix, which will take the time of n cube, order of n cube, right? So it becomes very expensive. And then there is the other problem that sometimes you might get Hessian matrix to be a singular matrix. In that case, the invert is not possible. So our whole thing collapses, right? So that's why we don't use this method, but there is a way to do this. Sorry, as I said, as I was saying, there is a possibility to go from this toward this direction directly, but it's not the best thing because it's too expensive and too unstable.
Another question. If there are local minimas, would it take us directly to the global minima?
No, it will once again take you to the local minima because, well, it will depend upon the shape of the derivative curve, but you see that I am in pointer mode or pen mode. Okay, so let's say you have some curve like this. Okay, if you take the derivative and plot it like a curve again, so for these points, okay, the derivative would be 0. So it would be something along this line. Okay, so it would be something like this, then back to 0. Wait, I went towards the wrong axis. Okay, let's use this thing. So for this particular point, the derivative would be 0, and then it will go up again, and then for this one again it would be 0, and then it will go up again, and then for this one again it would be something like this. So this will be the first derivative curve. Okay, so you will notice that get stuck at if we let's say start at this point. Okay, so at this point our derivative will reach 0, right? So our this thing would be 0. Okay, so now whatever Hessian thing we have, it won't matter because our weights wouldn't get updated then, right?
Yes, clear.
Okay, let's move on towards another form of update. This Newton method was just a side method. Okay, we don't use this kind of update because they are very expensive and unstable. But if we take the vanilla update, we can make some changes to it to make it to improve it. Okay, and one of the most basic changes is to add a momentum to the update. Add a momentum term. And what this momentum term does is that it takes into consideration the velocity of the updates. Okay, so let's say if at previous step I made the update of 0.5. Okay, at the next step I I don't want to make the update of let's say 0.01. Okay, because this will be a very drastic shift in the updates. Okay, and it's also uh, the other case also where we are going slowly and then suddenly we don't want it to make a very big jump. Okay, so it's kind of like a ball rolling. Okay, so there is some friction, which is this mu coefficient, which will be annealed over time, which can be annealed over time, but basically our next update depend upon the velocity or the value of the previous update. Okay, make sense? All right, and this is pretty simple. You will also notice that this also makes that so that we don't go from positive update and then negative update and so on. Okay, so this v would be our velocity. At the starting point, this v is just 0 when we start training. So our update would be just some friction coefficient, which we call mu or momentum. Well, no, this whole thing is called momentum actually. But this mu would be friction, and we multiply it with the gradient, and then we compute the velocity, which we add it to the weights. Okay, x represent weights here, right? But as we go along, so if at the first time at, fir- if at the first time step our v came out to be 0.2, so now our next update will correspond to whatever update we made earlier. Okay, make sense? Why we do that? Because we know that in the earlier stage we need to make bigger jumps, okay, to reach the convergence point faster, and then at the end we need to make smaller jumps. Okay? So if we are dealing with momentum, we can go in a very smooth fashion. So it's kind of like this. So which is the standard one? Yeah, the red one is the standard one, and then the green one is the momentum. You can see that the red one comes very slowly. Ignore the rest for now. The red one comes very slowly, but the momentum makes very big jumps and reaches faster. It does overshoot. It will always overshoot. Okay, but it can come back and go reach the optimal point faster, even if it overshoots. Make sense?
Yes.
All
Yes.
right. So now we have the momentum term, which just multiply the whole gradient with some term. Okay. To further, uh, to further make it more fancy, to make this update more appropriate, we can compute. You can think of it like a scaling or momentum for each of the terms instead of the whole thing combined together. Okay, so basically we keep track of a cache, and that cache is just the square. Okay, and then at each point we keep updating the cache, and then we divide the gradient at that point with the square root of cache. Okay, make sense? So as we keep training, the value of the cache keep increasing because we keep adding gradient to it, and this update will keep getting smaller and smaller. This thing is added here only to so that we don't get division by zero error. Make sense?
It's like kind of momentum squared.
It's kind of like that, but the main difference here is that in momentum we were multiplying the whole gradient with a single term. Okay? In here, each of this thing is actually a vector. So this cache is also a vector. Okay, or a matrix, whatever form your weights are. Okay,
Yes.
make sense? As its own cache, own momentum. Okay. So what happens with AdaGrad is that it will make jumps according to each of the magnitude of each of the weight itself, the gradient of the magnitude of the weight itself, and it will make bigger jump earlier, but it will also circumvent the problem of overshooting which we had with just simple momentum. Okay. As you can see here, this is AdaGrad, right? So it does make bigger jumps, but it doesn't make very extreme jumps as momentum does. Okay? And it reaches the convergence point faster. All right. Any questions?
This A, the grade, eliminate the need for normalization of the features.
No. That's something separate. Normalization of features, we usually need it so that our weights. So normalization is something different. We need normalization so that the value of our weights are not so much drastically different, or the updates are not drastically different. Let me just give you an example.
I remember from the deep
So
learning courses that if we don't normalize the weight space, feature space will be like ellipses, but in like more stretched. And if we
yes,
normalize, it will be like standard.
yes, yeah. That's one of deep normalizing. Well, it actually stands for the ellipsis thing. Is that let's say we have one feature which has the range from minus 1 million to plus 1 million. Okay, and then other one is from 0 to 1, right? The update for the and well, we haven't studied neural networks yet, but let's just consider a simple linear logistic regression or linear regression model where we have two weights. Okay, right? So the update of this weight would be much different than the update of this weight. Okay, so that's why we get ellipses, right? Now the problem here is that if if the scale of the gradient of one weight is very different than the scale of the gradient of the other weight, the updates will be very abrupt in one direction, right? And if we are using something like momentum, it will be very bad because it takes the whole thing altogether. Okay, Adagrad will somewhat solve it, but there will still be some problems with the update, with the judging of the update. Okay, so that's why we use normalization so that all the features are normalized, and then our weights are in some good range compared to each other. Does that make sense?
Yes.
All right. So the other question here is that what happens to the step size over time? As I said, if we keep adding to the cache, the size, the magnitude of the value of the cache keep increasing. So this thing will keep decreasing. Our step size will keep decreasing over time, right? Okay. Then we have another kind of optimizer, which is called the RMS prop optimizer, and it, it builds up upon Adagrad, where instead of just having the cache equal to the square of the gradient, okay, we have a we do a soft update of the cache, okay, instead of doing the hard update. By soft update, I mean that we keep the old value and then we add the new value, then we add the fraction of the new value. Make sense?
Yes, cumulative.
Yes, kind of cumulative. Yeah. So basically the only difference or the only change is that how we compute the cache. So here it was just the square of the gradient. Now thus it's multiplied with some decay rate. Okay.
Okay.
Any conclusions about
Why we
this?
do that?
Uh,
Is there a problem with
why we do
Adagrad?
that? The main problem here is that, for example, if if the gradient update is too large at some point, okay, and then we do the cache this way, this might will actually come up to be small, right? Let's go back to
Yes.
that. So there it is, RMS prop. RMS prop actually will actually move slower than AdaGrad, but you will see that it will have less uh, of an extreme jump at any point. You will still notice that it's not that RMS prop is always better than AdaGrad. It depends upon your particular thing that you are doing. But in general, RMS prop will perform better than AdaGrad. Does that answer the question? The main advantage here is that, for example, at some point, if let's say uh, you were at a wrong location, okay, and the update was bad, right? So let's say you were like this, and the model told you to go here, okay? But so if you were using this cache as it is, uh, this would have made your cache bad. Okay, but if you are doing soft update that you don't extremely update the cache, you just make a slight update to the cache. So even if you make a wrong step, you have a better chance or better probability or better way to get back towards the right direction.
Yes.
Okay, so the concept of soft update is actually very common, and it just basically means that, for example, if if at one point I was at the value of 1 and now I need to go towards the value of 3 instead of going directly towards that, okay, the first step. Then I maybe go towards 1.9. So I go towards 3 in some increment instead of just directly jumping towards 3. Okay. Uh, this is just the explanation of RMS prop. You can read more about it in this Jeffrey Hinton's course or in his book, this paper. Book, sorry. Okay, this is just the same example. We have already seen that. Any questions so far? Okay, let's move on towards one other optimizer, and this is actually one of the very common optimizer mostly used, and this is called Adam. Okay, you can think of Adam like in the way that it merges both the momentum and the aldehyde. Okay, so we have two terms. The first term is this M term, is a coefficient called beta 1, and this thing is similar to momentum. And then we have the second term V, we, which actually works something like a cache. So you can see that it has the same uh, square of the gradient, right? And then we have the square root of the cache. We multiply the gradient uh, with the m. Sorry, divide the cache divide the m term by the cache and then add it to the weights, right? So this first thing is like momentum, and then this thing is like ADA grad or RMS proc like. Any questions?
Why
One of the
the bias correction?
Yes, I was just going to come to that. Why the bias correction? Because at the starting point we initialize m and b to be 0. Okay, so in the beginning the value of m and b are not what they should be because we don't know what value they should be, right? Okay, so in the first term, in the first few terms, we actually decrease the uh, weightage of these m and b terms, all right? And then eventually, when our time step increases, uh, this thing becomes very close to 1, okay? So then it doesn't make much of a difference. So this beta 1 is a value smaller than 0, oh sorry, smaller than 1. So if you take exponent of value smaller than 1, it decreases, right? So eventually this whole term will become close to 1, and then MB and then NBB won't make much of a difference. Okay,
Yes.
everything clear? Any questions? All right. This we already discussed earlier. I already mentioned that learning rate is still very important, although these optimizers somewhat help us with set learning rate is very bad. They can't do anything because you see that in all the expressions we still have learning rate in them, right? So the choice of learning rate is very important, and it's better to stay on the lower side than the higher side because the higher side can actually lead towards degraded performance, but with the lower side, we will eventually uh, get towards the optimal state, but just slower. Of course, it would be best to have the learning rate which is the optimal state faster and does not make any erratic jumps. Right? All good?
Yes.
Okay. One last thing that we will discuss is as I mentioned, something called learning rate schedulers. We use learning rate schedulers because, as I mentioned earlier, uh, at the beginning of training, we are very far from the optimal point, so we can or we should make bigger jumps, okay, so that our convergence is faster, right? But as we reach closer and closer to the optimal point, we should actually start reducing our jumping size because now we don't want to overshoot the optimal point, right? So to rectify this thing, but we have something called learning rate scheduler, where we decay the learning rate through some strategy. Okay? This strategy can be very simple, like for example, every 10 steps, I will divide my learning rate by 10. Okay, this is one strategy. Another strategy could be exponential decay, where I take the negative of the exponent of the time step and then multiply that with the learning rate. And then there is another one which is most commonly used is something called cosine decay, where I just take the cosine of the time step. Okay. Of course, there is the whole expression involved with it. We can also specify what should be the maximum and the minimum value that because we don't want the learning rate to decrease so much that it reaches zero, right? We can set the rate of the decrease and the stuff like that. So there are different kinds of learning rate schedulers. The most basic one is the step scheduler, where I just take a step at a fixed number of epochs. We have exponential decay, cosine decay, polynomial decay, staircase, and so on. Yeah. Any questions? Confusions? Perfect. Okay.
How did they decide that cosine decay is the best? Doesn't it differ from like one algorithm to other based on like the data and the goals of the model?
Uh, the main reason is, of course, empirical validation. Okay, because when they tried it, they found that it works the best. The other reason you can somewhat uh, guess it from this graph. Okay, you see that for example, let's compare exponential and cosine decay. Okay, for the exponential decay, where is exponential decay? I don't think there is exponential decay here. Okay, let's compare this polynomial and cosine decay. Okay, you notice that for the polynomial decay, at the earlier steps, the learning rate decreases very fast. Okay, but in the earlier steps, we actually don't want the learning rate to decrease that fast, right? Because we can afford to make big jumps. Okay, but cosine manages it quite efficiently. So at the very beginning, it has a slow decrease, and then it decreases a lot faster. It becomes very steep, and then at the end, once again, it reaches a slow decrease. Okay? So the behavior is quite uh, close to what we actually want our learning rate to look like. So that's why this cosine performs the best, or that's why we say that it is the best.
Okay. Yeah, makes sense.
All right. Anything else? Okay. Let me just summarize everything. We discussed different kinds of optimizers today, and we started with the simple gradient methods. We had the vanilla gradient descent, and there we said that okay, instead of dealing with the whole data set, we can do something like mini batches or stochastic gradient descent. And then we also discussed the second order gradients, which help us get the direction better, so makes the convergence faster, but they are very expensive and unstable, so they are not practically usable. And then we have the updates with momentum, where instead of where we rely on the velocity of the previous updates to make the next update. Okay. And then we added AdaGrad and RMS probe to diagonally scale the gradient so that each of the weights are scaled differently according to their gradient magnitude. And then Adam, which does both things, which scales and also applies the momentum. Okay. Any questions about any of these?
Clear.
All right. This is just another example. You see how momentum goes towards the wrong direction. but RMS prop and Adagrad are much better towards that. By the way, this NAG is another form of momentum optimizer, and it uses something called look ahead. So basically, at each step, it actually computes a gradient for what it would be in the next step and then make an update. So it does slightly better than the vanilla momentum optimizer. Okay. All right. That's it for today for the lecture part. Any questions?
I do have a question, but it's kind of out of the lecture. So
Sure,
I want to
sure.
ask it last one.
Please go on. Anyone else in the meantime?
No, it's clear. Thank you.
Everyone is clear? All 96 people. Okay. I hope you enjoyed the lecture and learned something new. In the afternoon, we will have the practical session, which one of the TAs will conduct. I will, of course, be present there, and if you have any questions, please feel free to ping me. And after that, since we are done for the day, we won't have any other session after that. Okay. If you don't have any questions, Ans, please go on and ask yours.
Dr. Muhammad, I want to talk. I want to ask you about Javier initialization. I actually struggled to understand why it works. Why is it better than random initialization? Why does it always better than random initialization?
Hmm. I'm not familiar with the form of Javier initialization. Let me have a look. Oh, by the way, I wanted to share some resources with you. Let me do that too. You can see my screen, right?
Yes.
Okay. So this one is for, let's move on to this one first. Okay. As I mentioned earlier, that softmax sigmoid is just a special case of softmax, right? So if we have only two classes, then softmax just boils down to sigmoid. Okay? Try thinking about it, but if you can't, uh, this this page very efficiently highlights the importance of uh, softmax, why is it needed, and how sigmoid boils down to max. So I invite you guys to read it. And then this one is about harmonic mean. If you aren't familiar with it, which reminds me, I also wanted to show you something else about F1 squad. Yeah. Particularly this diagram, I really like this diagram whenever I'm explaining the Persian and recall. If you have a look at this, then you can quite clearly see what each of the Persian and recall means. Okay, so Persian is just basically how many retrieved items were relevant, and then recall is how many relevant items were retrieved, and it also tells you the difference between two positive, false, negative, and two negatives. Okay, this one because you asked the question about gradient boosting. This page very efficiently explains about boosting and gradient boosting and different variants of it. Uh, please go over it if you have any, if you want to know more. And then lastly, this one is about mag. It explains the look ahead term I mentioned earlier. All right. Okay. Let's look up Javier initialization. Oh, okay. So basically, you know that how are you uh, familiar with how neural network works?
What did you say?
Are you familiar with how a neural network works?
Yes.
Okay. So in and fan out terms. Okay. This fan in means how many from from how many neurons this particular
Yeah.
neuron or the next neuron will get inputs,
Mm-hmm.
and then the fan out is that how many neurons it will go outwards. Okay. So if I add a new slide here, go to the slideshow again. Okay, so let's say I have a neural network like this. I have four weights here, two here, and sorry, not weights, neurons, right? And three here. Okay, so the weights would actually be the connection between these. Okay,
Yes.
these are the weights. Now the problem is that let's say this layer had a very high number of weights. Sorry, a very high number of neurons. Let's say 1,000.
Mm-hmm.
Okay, and if
Mhm.
I just randomly initialize the weights, like like with zero mean and 0.01 standard deviation. Okay, in the first few iterations, these neurons both these neurons will have very high values, right?
Yes.
Because the values of these neurons is actually the sum of all these weights, right? Multiply,
Yes.
of course, by the previous features. Okay,
Yes.
and so that's why they introduce this fan in and fan out terms. So if the previous layer has a very high number of neurons, so these weights are then initialized with a low value so that the overall value of this neuron doesn't get exceedingly high in the first few iterations.
Okay.
Okay,
Yes.
makes sense. Makes sense. And for the same reason, they have the fan out term. So fan out would be that how many neurons that this neuron will go into. Okay, so if it is going into very large number of neurons. Okay, so then these weights would be smaller according to my previous Feynman explanation, right?
Mhm.
So then I can afford to have a higher value for these neurons. Okay, so that's why I use both the fan in and fan out to determine uh, what should be the value, what should be the range of the initialization of these weights, so that none of the values of these neurons exceed or go to a very high value in the first few iterations. Of course, eventually when the neural network trains, they will come down towards the optimal value, the weight, the weights I mean. But if they are not initialized properly, then it will take them longer time. Okay.
Yes.
Also, weight initialization also sometimes improves the performance because it helps us ignore the local minima. Sometimes it can help us ignore the local minimas.
Mhm.
Okay. Does this answer your question?
Yes, I actually also understood that how it adapts to different architectures.
Perfect.
Thank you.
Okay. Any other questions? All right then. Thank you for listening to me. I hope you enjoyed the first half of the day and learned new things. We will see you guys in the practical session. And of course, if you have any questions at any time from me, please feel free to ask and I'll be here. Okay? Enjoy your lunch, enjoy the prayer time, and we will see you at 1:30, right? Can one of the TS please confirm this? Mohammed, Hiba, are you there?
Yes, that's correct. At 1:30.
Okay, perfect. All right, guys, see you guys at 1:30. Assalamu alaikum.